Differentiation video 5, stationary points. And for those who sometimes, like me, get a wee bit confused on these things, station, A-R-Y, stationary, all right, meaning not moving, as opposed to stationary, E-R-Y, which means pens and paper and pencils and stuff like that. But of course, most of you will be smarter than me and know that already. Anyway, stationary points. That's points on a curve or on a graph. By definition, if not moving, that means for us, stationary points, mathematically speaking, are points where the gradient is 0. The graph is not going up or down at that instant. So, little copy please of a diagram like this in page 7 of your notes. Add this in. 3 points marked here in Roman numerals, this one down here. And again, I've just drawn in the gradient at that point, so it's a horizontal line, gradient 0. Here, just momentarily, the curve is going up, just going horizontal for an instant, and then continues going up. And here, rising to a point and then going down again. So, stationary points, point 1 here is, well, it's coming down to minimum value and going up again. So we say it is a minimum turning point. And you can call it a min TP if you wish. Okay. Point number 3 is a maximum turning point. And people often think, oh yes, stationary points are the same as turning points. No, they're not. Turning points are minimum and maximum are an example of stationary points, but we also have number 2 here. And number 2, where it goes in and then continues up, or perhaps comes down and then continues down, that is known as a point of inflection. More old-fashioned books will spell this with an X as opposed to a CT. Okay, but either is acceptable. All right, but a point of inflection, falling or rising. As I say, more old-fashioned books spelled with an X. You know the word connection used to be spelled with an X? Something I've just learned. Anyway, so we can have, as I say, a minimum TP. And if you write that, everyone will know that we're talking about a minimum turning point. And down here, maximum turning point. But point of inflection is normally written in full. These 3 examples are examples of the nature of the stationary point. So if a question asks you, what is the nature of the stationary point? They want you to state either that it's a minimum turning point, that it's a point of inflection. Doesn't matter if you say if it's rising or falling, but as long as you state it's a point of inflection, or that you state that it's a maximum turning point. So in your notes, right, on page 7, where it says stationary points, brackets, turning points. Turning points is an example of stationary points, but it's not the only kind of stationary points, so that should not have been there. Underneath this bit here is where you can do the diagram and the different examples. Turning points, maximum, minimum, and also, as I say, points of inflection. So let's look at a little example then. Questions will often ask you to find the coordinates of a stationary point and usually also to find the nature of the stationary point. Let us consider, this is on page 8, but y equals x squared minus 4x cubed plus 3. Okay. Step 1. Well, let's find a formula for the gradient. And it certainly used to be that sometimes just for writing down f dashed x, which some people do and prefer, if they say when is the function not rising or falling, but if you wrote something here to indicate that you're differentiating, the very fact you wrote that got you a mark. Another mark for working out the derivative. Now that is certainly, it's debatable as to whether you still get a mark for writing dy by dx. You certainly get a mark for working out the derivative. So in here, of course, this will be easy for us by now. 4x cubed minus 12 x squared. And the plus 3, of course, differentiates to 0. Next mark, which people often forget to write down even though they know that that's what they're doing. Write down the derivative again and say, because it's a stationary point, our gradient equals 0. So you get a mark for setting the derivative equal to 0. All right, now we have an equation to solve. All right, and we know how to solve something like this. Step 1, factorize. Okay, and again, when we're factorizing, always look for a common factor first. It will make it much easier. So if I look at these two terms here, I've got a common factor. They both divide by 4, certainly. And also both terms divide by x squared. So I'm going to take the x squared out, and that's going to leave me with x, take away 3 in my bracket, equal to 0. Again, there will be those out there who keep forgetting to put equal to 0, and then suddenly it will miraculously appear towards the end. Write equals 0 down to keep it mathematically correct. Two terms multiplied to be 0, so one of them must be 0. Either 4x squared equals 0, which is x squared equals 0, x must be 0, and 0 is not plus or minus, so I don't need to worry about what about the two different kinds of square roots. Or my second term is 0, my x minus 3. So x must be 3. So these are the two places that are going to give me stationary points. In my first equation, remember my first equation tells me points, but these are the two values that make my second equation, my gradient equation, equal to 0. We're not finished yet though. The question said find the stationary points. That means both coordinates. So we've differentiated. We've set equal to 0. We've solved by factorizing nearly always. And then let's get the y coordinates. So I'm going to say for y, x to the power of 4 minus 4x cubed plus 3. Because y equals this, so for x equals 0, that gives me y is 0 to the power of 4 minus 4 lots of 0 cubed plus 3. Oh, that's just 3. So one stationary point is at 0, 3. Make sure you write it as a point. And then again, for x equals 3, y will equal 3 to the power of 4 minus 4 lots of 3 cubed plus 3. If you work that out, equals negative 24. So again, I'll state that point. That's the point 3, negative 24. These are the two places on my graph where the gradient is 0. So these are my stationary points. Now, it is very unusual in the exam that that would be the end of the matter. If it said find the stationary points, we've done that. But nearly always, they will also ask us what is the nature of the stationary points. And to do that, we make what is called a nature table. Here's how that works. Set up a little table like this. The first line, I'm going to put in x values. My second line, I'm going to consider the gradient. You can call this, now I'm going to put dy by dx because that's my preference, right? Often if it's talking about functions, and it's certainly in textbooks, they'll call this f dash x. And so we'll just put in m, because I say we're talking about gradient, and I prefer to use m for gradient. It does not matter which. So anything here that indicates gradient, whether it's dy by dx or m or even f dash x. And then down here, I'm going to talk about the slope, or some people put in the word line there. You'll see why in a little minute. And over here, I'm going to do the same thing again, but I'll do that in a moment. My first answer, my lowest answer, was when x is 0. So my x value, I'm going to look at what happened when x was 0. Well, the gradient was 0. If it's not, then there's something wrong. We can go back to our gradient equation and check. 4 times 0 cubed minus 12 zeros. Yes, that's 0, so this is fine. So what's the slope doing at that point? It's horizontal. What's happening before or to the left of x is 0? Now, often in tables we'll mark this with something like saying there. What's happening before x is 0? So this just means to the left of 0. Well, let's consider. Here's my gradient equation. Pick a number less than 0, so you can choose -1 or -2. I prefer to go much larger in size altogether. I'm going to say -10, because when I say -10, 4 times -10 cubed, that's 4 times negative, that's -4,000. Take away 12 lots of -10 squared, well, that's going to be 1,200, but it doesn't really matter if I'm adding or subtracting it, because I'm already at -4,000. So this bit is dominating everything because it's a higher power. But anyway, when I put in, or even if you do just put in something like -1, it'll be 4 times -1 cubed, take away 12 times -1 squared. We get a negative answer, and I'm not concerned with the exact value, just whether it is positive or negative. So it is negative. So in here, and most books just put a minus sign. I prefer putting a little negative, probably because of the physics part of me. Put a little VE on the end to say negative. So the slope is going down at that point. Now I'll do the same thing for just past 0 going positive. To the right, that means of my 0 value. It's called finding the local values of the gradient. So what's happening just to the right of 0? Again, I can put in any number here. Oh, but not more than 3. I'm looking at what's happening between 0 and between x is 0 and x is 3 from this value here. So I must pick a value more than 0, but I don't want to get up to 3 because that's going to be a whole different thing there. All right, so I'll just pick 1. Or you could pick 2, but I'm going to go with 1. Nice, easy number to work with. Look at the gradient. 4 times 1 cubed. Take away 12 times 1 squared. So that's going to be 4, take away 12, -8. It's a negative answer. So in here, this is negative again. So it's sloping down again. And I can see from this table, my line is coming down, along, down. That's a point of inflection. So I can say a point when x was 0, and when x was 0, we've already said that was the point 0,3 when we worked out the y-coordinate. 0,3, we can have to state, is a point of inflection. That's the nature of the point of the stationary point 0,3. Now, that's that point dealt with. But of course, we also had what happens when x is 3. All right. Well, make up another little table just the same. X, and when x is 3, my gradient and my slope, or my line. So, when x is 3, the gradient is 0. If we have time, we'll do a quick little check. 4 times 3 cubed, take away 12 times 3 squared. Okay, actually works out to be 108, take away 108. So yes, it's 0. So at this point, just for an instant, that's the slope. What's happening to the left of 3? I have to pick a number less than 3, but again, more than 0. I'm looking at what's happening after we've got past the 0 coordinate, but before we get to the 3 coordinate. Well, actually, I've already got a set of answers here, because we said, well, we tried the number 1 and we found out that it was negative. So I'll just use these results again. And that meant the slope was going down, because whatever number I pick between 0 and 3, I can use the same results twice. What happens beyond x is 3? Well, that's known, we mark that as 3 plus, just means past 3. So again, I'll just look at an extreme example. I'll probably pick 10, but again, you could choose 4 or 5 or 3.1 if you wished. But anyway, I'll go with 10. 4 times 10 cubed, that's 4,000. Take away 12 times 10 squared, take away 1,200. 4,000, take away 12. Oh, okay, I can see the 4,000 again is going to dominate, so it's a very positive answer. So I'm going to put in here, that's positive. And so this time my slope is going up. So I can say, oh, it's going down, along for an instant, and up again. That's a minimum turning point. So I will say that my point, my second stationary point, which was 3, negative 24, is a minimum turning point. And if I just want to write min TP, that's perfectly acceptable. This is us done in terms of what the question normally asks, but I wanted to show you one little extra thing. Many people like to write their tables separately here, but as I say, you must remember that when you're trying a value here to see what happens 0, make sure it's a number less than the next stationary point here when x is 3. And you can use the same results twice. So in fact, what many people do is they say, well, actually, I'm just going to combine these two tables together. And they get a table like this one. They say, I'm going to have x, I'm going to have my gradient, I'm just going to do m for speed now, and my slope. And they say, here is my first stationary point. Make sure you put the smaller number first. Here is my second stationary point. Right, my number is less than 0. And that was 0, and that was horizontal. And this we already worked out was negative. So that was slope going down. Between 0 and 3, do you mark it as 0 plus or 3 minus? You mark it as either, or sometimes I just put an arrow like that to show that I'm going from 0 to 3. But again, we worked this out up here. We said this was negative. That was that. We said this was 0, which gave me horizontal for an instant, and past 3. Again, some people occasionally put arrows up here too. That's okay. This was positive. And there. And so they look at this and say, there's my point of inflection. There's my minimum turning point, and it's just marginally quicker than writing it out like this. But I would like to add one thing here, which you are also sometimes asked. The question will sometimes say, when is the function decreasing? And when is the function increasing? In which case we'd probably have here f dashed x, but that doesn't matter. When is the function decreasing? Well, it's decreasing when the graph is going down. So it's decreasing here and here. So I'm going to say it's decreasing. Of course, you could normally write the function as decreasing. If you were asked, which won't be in today's exercise, but next time, decreasing for, well, when is this? This is when x is less than 0. X less than 0. It's also decreasing here. Now, please don't just say, oh, it's decreasing for all x is less than 3, because at this instant, it's not decreasing. It's decreasing here and here, but momentarily at x is 0, it was not decreasing. So we're saying it's decreasing to the left of 0 when x is less than 0. It's decreasing between 0 and 3. So I'm going to say it's decreasing between 0 and 3. So if I write it in between, if I'm not sure of my signs and so on, I'm going to write x, there we are, is in between 0 and 3. I write the smaller one first. Now, if I cover up the x, I've got 0 is less than 3. Because people sometimes get like a mixture of signs in here. That means if 0 is less than 3, I'm going to use the less than sign all the way through. So this reads 0 less than x less than 3, but it just means x is in between 0 and 3. That took care of this bit and this bit. Oh, and finally it's increasing once x gets past 3. So I'm going to say the function is increasing for x is more than 3. Now you can get, of course, all that information from here. Here we are, decreasing for less than 0, decreasing between 0, but I have to jump over here to 3, and increasing for more than 3. So that's another reason, once you're comfortable with it, and if you wish, to combine it into one table with the different stationary points. But please remember, we differentiate and say we're doing that. We get the derivative. We set that this derivative is true for any value of x. Then we're looking for the particular values of x when it's equal to 0. So write equals 0, scores marks. Solve it, usually by factorizing. Get your different x values. Get the corresponding y values so we can state our stationary points. And then use a nature table by looking at either side of the stationary point as to what happens to the graph to say is it a point of inflection or a minimum turning point or indeed a maximum turning point, and state those things. Having done the nature table, which scores marks, you also get marks just for writing and interpreting the table. It's a minimum turning point, it's a point of inflection or whatever. And last but not least, if the question says when is the function, right, when is the graph decreasing, you need to be right just by looking at the slopes of your nature table in the end. Going down, decreasing, be able to specify less than or in between, like here, or more than.